All right, here we go. Let's take a look at part 2 of trig identities. We're going to look at the sum and difference identities today. And today's Valentine's Day, which is pretty awesome. And I was just thinking, man, I love me some trig identities. So that's my Valentine's, some trig identities. That's awesome. Let's do these bad boys right here. So really, we got some big formulas to talk about here. So what are we doing? I left them blank because I want you to write them in here. But we're actually going to start adding and subtracting two different angles. So I have angle A and angle B, or angle alpha and angle beta. And really what we're doing, I know we don't use degrees in here, but just to kind of show us what's happening, I want to know the exact sine value of something like 45 degrees, because I know that one's on the chart, and maybe 30 degrees. So what's cool is we can actually add them together and say, hey man, that's just saying the sine of 75. Well, 75's not on the unit circle, spoiler alert. But with this handy dandy formula, we can actually find the exact value of 75, which is going to unlock a whole new world of trig identities, exact values. So we can subtract them and maybe find the cosine of 15. So that's where we're kind of heading with this. So what is the formula? So if I have these two angles I want to add together, here's how the formula goes. Write this in. So we're going to take the sine of the first angle. We're going to take the cosine of the second angle. So we're going to times it by the cosine of the second. And then we're going to add the sine of the second angle, beta, and cosine of the first angle. This magic formula is going to allow us to add them together. And then if I want to subtract them, it's the same thing. So this notation here, first angle is alpha. So it's the sine of the alpha, cosine of the beta, or the sine of the first, cosine of the second. Since you're subtracting them now, what do? We just subtract in here. So the formula is pretty chill. It is one you're going to have to know and memorize. But when you write it down enough, you just kind of know it. Excellent. So what about cosine? So same thing, if I want to find the cosine of 15 degrees, let's say, or it'll actually be in radians, but this formula is a little different. How's this one work? This one I like it. This one's I can think is nice to remember. It's going to be the cosine of the first angle, cosine of the second angle, and then what are you going to do? It's the opposite of what you would think. So if you're adding here, you're actually subtracting here. And then this will just be the sine of the first, sine of the second. Awesome. There it is. Fill that bad boy in there. And the second angle here is beta. And then come down here with the difference. If I want to subtract them, I'm going to do the same thing. I just really want to write them all out. Cosine of the first, cosine of the second angle. But remember, this is subtraction. So what do we do with cosine? It's opposite. We're actually going to add it. Excellent. So these are the formulas that allow us to do these things. So let's go ahead and do one real quick, and then I'm going to show you why these formulas work, if that's coolio. All right, here we go. So let's find the exact values of this. We're going to take these two angles together, pi over 4, 5 pi over 3, add them together, and we're going to find the exact value of that. So again, this is not on the unit circle, but the parts of it are. The parts that are adding are actually in the unit circle. So I jotted the formulas down here so we can use them real quick. So if I'm adding these two angles, this is like my alpha, this is my first angle, this is my second angle. And I like to write it all out, man. Let's write this bad boy out. So the rule is what? We're adding them together. So we're going to take the sine of the first one, so the sine of pi over 4. Cosine of the second one, so it'll be the cosine of 5 pi over 3. Like this. And then we're going to add them, and I'm going to say what? It's the sine of the second angle, so we'll take the sine of 5 pi over 3. And then it's the cosine of the first angle, which is going to give us what? Pi over 4. There it is. So write that out. Now it's just a matter of using the unit circle. Pull that unit circle up here. So I've got one right there. And we are just going to find the values in here. So what is the sine of pi over 4? So remember, we're looking at pi over 4. We're looking at the sine value of that is going to be radical 2 over 2. And this is all times in here. You know, I didn't write the times, but we're timesing these together. So sometimes I like to use parentheses just to make sure my signs are cool, the positive negatives. We're going to times that by the cosine of 5 pi over 3. So where's that bad boy? So that is going to be all the way over here in this quadrant down here. And the cosine value is positive. And so we're looking at 1/2. Awesome. And then we're going to add together what is the sine of 5 pi over 3. So that's the other, not the 1/2. Sine is negative, so be real careful of those negatives. This will give me negative radical 3 over 2. Awesome. Then the cosine of pi over 4 is also radical 2 over 2. So hopefully our unit circle is getting pretty awesome by now. We're using it so much, it's getting pretty smooth. Let's multiply these together. What do we get? Multiply across the top, we get radical 2 over 4. And we're going to add that to what? Multiply those together. this actually turns into a negative. Radical 3 times 2 is negative radical 6 over 4. That's pretty cool. They have a nice common denominator, so we're going to make it one fraction with the denominator 4, and then on top we're going to just say radical 2 minus 6. So you're going to see this answer a lot. This little radical 2, radical 6 thing, it's just a matter of making sure our signs stay straight. That is actually the exact value. If I add those two angles together, that's the exact value you get. Awesome. Okay, before we start this problem here, where these formulas come from. So I just want to show you real quick that I just didn't make these up, and that was just kind of rude that I just made up some formulas. So I'm going to show you the proof. I'm going to play it in like ×2 speed, so don't write it down. Just watch it. Just enjoy it. Like maybe get some popcorn. Watch this little proof. If you're really interested, just slow it down, and you can go. It's not often you slow down these videos, but you can slow it down and watch. But I'm going to go quickly through it just so you can say I didn't make these up.
The goal is to prove what happens when I subtract or add two angles. So I'm going to start off with subtracting an angle. So let's start off with this blue angle here, and I'm going to say this angle from here to here is alpha. So I've got alpha right there, and then in red I'm going to draw another angle. I'm going to call this one beta. So this is beta, and the other angle in blue was alpha. So that's great. So what I want to do is subtract these two lines. If I subtract the distance, I can find the distance between alpha and beta. So I'm looking for that distance. So ideally, if I want to make up numbers, if you're more of a concrete person, this first angle could be like 140 degrees, and then I want to subtract another angle from it. Maybe I'm subtracting 120 degrees. Obviously, what comes up? 20 degrees. So if I subtract these, then I get a new distance over here. That would be like my 20 degrees. So what is this angle? This angle is actually alpha minus beta is that angle. And again, the distance between this and 0 should be the exact same. It's this distance. We're subtracting, looking for a distance. So that's the basis of this whole proof. You're subtracting two angles, and really that's the gist of this. If you understand what we're doing, we're subtracting two angles. What we're going to look for is finding exact values now. So here is the proof. Get ready. This is fantastic. All right, let's start with the coordinates of this. This point right here, the xy coordinates. I'm looking for these coordinates. Well, I can use my trig function. X is cosine, so that is really the cosine of alpha, comma, the sine of alpha. So those are my coordinates. Those are my xy coordinates for that angle right there. How about for beta? Same thing. If I want to find this point right here, the x value is cosine beta, the y value is sine beta. So depending on the angle, if I type in my calculator, that'll tell me the number there. The one that looks weird though is this one. This angle is actually alpha minus beta. So what are the coordinates of this point right here? Well, you guessed it. It's the cosine of alpha minus beta, comma, the sine of alpha minus beta. So it looks intense, but that's our ultimate goal. We're trying to prove that this is the identity. What happens when I subtract them? So all we're going to do is show that this green line over here is congruent to this green line over here. So if we're going to do that, how are we going to show that? Well, we're going to use the distance formula. Remember the distance formula? Distance is just the Pythagorean theorem. We're going to subtract our x's and square them. Then we're going to subtract our y's and square them. So if we do that, some people like to put little numbers here. If we like to do that, that's why I have these coordinates. So I'm going to subtract blue and red to get this distance, and I'm going to subtract black. And what is this point right here? Well, this point right here is over 1 up 0. So that one should be easier. Let's start with blue and red. Let's go for it. Going for the glory here. So let's do a distance formula of, let's see, it's going to be the square root. It's going to take some room here. I'm going to take my x value, so cosine alpha minus cosine beta. So cosine alpha minus cosine beta, square it, plus I'm going to do my y values, and we're going to be sine. So sine alpha minus sine beta. Oh, this is so fun. I love it. So that's the distance between those two. Can we simplify this? Sure, we can FOIL this out a little bit. I'll change colors here. But we can't FOIL this out. It's going to be what? Cosine squared alpha. I may have to slide that over. I think it's going to take some room. Cosine squared minus cosine alpha beta. Then I'm going to have another minus inside term. I actually get 2 of them minus cosine alpha beta. So it's a difference of squares here, so I get 2 in the middle. And then my last one, cosine times cosine, was going to give me the plus cosine squared beta. Holy cow, that's the first part of this. Let's slide it over. I'm going to need more room, I think. All right, so keep this rolling. What's the second part? Well, I'm going to add, same thing here. I'm going to get sine squared when I FOIL it out. Sine times sine alpha times sine beta. And I'm going to have 2 of them, so I'm going to have 2 sine alpha betas, or 2 sine alpha, 2 sine beta. Then do the last term, it'll be plus sine squared beta. So that is just FOIL property right there. What's cool about this, though, is anything good happens from this. I hope so, because that's a mess, and I don't want to do much more. Check this out. I have a cosine squared here, and a plus sine squared here. What happens when I combine these two together? It's a property, yeah? Cosine squared plus sine squared is what? It's 1. Awesome. And it's alpha, they're both alpha. But check this out. Cosine squared beta, sine squared beta, what happens with these guys? They're also equal to 1. So really, if I add those together, I'm going to get what? 1 plus 1, 2. So that is actually 2. Unfortunately, that's as far as I can simplify it. This cosine alpha, cosine beta just comes on down, and then minus that 2 sine alpha, sine beta. Fantastic. And really, technically, this is the distance, and I'm square rooting it all. So that's as far as I can simplify the first part. That is this line up here. So I just found, let's say, D1. That is the first distance. Let's find D2. I love it. This one is going to be based off of this point right here. So D2 is going to start with, I'm going to give myself lots of room for D2. Here's my x value. Here's my y value. So it's going to be cosine of alpha minus beta minus the x value of that. That's just going to be 1. And then I'm going to square it. Plus, I'm going to do, what? Sine of alpha minus beta minus the y value of this point. I'm finding this D2 right here. Here's D2. So I'm finding that, and that's going to be minus 0. And I'm going to square that. Fantastic. So again, I got to do a little more foiling for D2. Let's FOIL this up. I'm going to end up with cosine squared alpha minus beta. Distribute there. I'm going to get minus 1 cosine alpha minus beta. If I do this one, then I'm going to get minus 1. So, well, this is a perfect story. I'm just going to get 2 of these. And then I'm going to go plus 1 at the end. Negative times a negative. So if you want to expand that out and multiply it, feel free. But I'm just foiling it. This one feels great because that's just 0, so I'm just going to end up with sine squared alpha minus beta. Holy cow, look at this screen. I love it. You can call your parents over and be like, hey, look, we're doing math today. But this will look better. It'll get better here in a second. We're going to need some more room, though. Okay, so give myself a little bit more room there. So again, this is still square root of all this in a distance. Does anything cancel in there? Did anything good happen at all? Actually, something does happen, doesn't it? Check this out. We've got cosine squared plus sine squared. They're the same angle, just like it's 20. It's alpha minus the beta. So these are Pythagorean identity. Those equal 1. And I already have a 1 in there. So check this out. I've got 2 minus 2 cosine alpha minus beta. Fantastic. And that's distance 2. And it's the square root of that. So we're doing great here. Very good. So we've got D1, D2. What I'm going to do is I'm going to set distance 1 equal to distance 2. That's our whole goal to show they're the same. And I'm going to go ahead and square both. They're both square roots, so I'm going to square both sides. So if I can do that in one lump sum, I think that'll help me out here. So I'm going to bring down. Let's bring D2 on the left. I've got 2 minus 2 cosine alpha minus beta. And this is my whole goal. I'm looking for a different identity. I want to get cosine alpha minus beta by itself. On the right side, I'm going to have 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Still barely fits. I'm just bringing this down as my other distance. What's good about this? I see a lot of 2's in there, so that seems like it's pretty cool. So hopefully I can do something with my 2's. In fact, I can. If I subtract them from both sides, right off the bat, what's going to happen? Minus 2, minus 2. These guys are just gone. Then what else am I going to do? Well, this is negative 2 left over. I'm going to go ahead and, do we need more room here? I'm going to divide that by -2. Whatever I do to one side, I got to do it to the other. Divide that by -2. So these will cancel. Here's my final identity. You can fast forward to this point. Cosine alpha minus beta. What do you get when I divide this by -2 and divide that by -2? I'm going to get cosine alpha, cosine beta, minus sine, not minus plus, negative divided by negatives plus, sine alpha, sine beta. That is as far as we go. That is the identity. That is amazing. Holy.
Awesome. So that was super cool. Hope you enjoyed that. So now let's use them. So the formulas do work, and we can prove actually cosine and tangent. We can actually keep going, but for our class, we're only going to need no sine and cosine. So let's try this one. So for cosine, I know it's going to be what? It's going to be the cosine of the first angle, which is 7 pi over 4. And I'm going to times it by cosine of the second angle, which is 2 pi over 3. Now it's the opposite sign. That says minus, so I'm going to plus. I always do the opposite. It's going to be the sine of that first angle over the sine of the second angle. Awesome. So I do like to take the time to write that out. I just think we make less mistakes if we're going to write it all out here. And now we're going to go through, let's pull up the unit circle, make sure I'm in the right quadrants here. And I'm looking at what? 7 pi over 4 is back over here in that fourth quadrant. So I'm down here. And I'm in this positive, negative quadrant. So cosine's positive. Anything with 4 is going to be radical 2 over 2. And I'm going to times that by 2 pi over 3. So where's that bad boy? That's going to be up here in this. Whoa, that's not a very straight line. Let's try that again. It's going to be somewhere up here in this quadrant. So I've got the negative, positive going on. So cosine is actually going to be -1/2 here. And I'm going to add the sine of 7 pi over 4. So this is where that sine's negative. So we're going to have negative radical 2 over 2. And then 2 pi over 3 is the other half of that. It's going to be the radical 3 over 2. And it isn't positive in that quadrant. So you got to make sure you get your signs correct here. Now, once you have that, multiply across, what are we going to get here? It looks like we're going to get negative radical 2 over 2. We're going to add, I'm sorry, not over 2, rookie. Let's try that again. Negative radical 2, what is 2 times 2 on bottom? It's 4. I don't want to go too quick here. And then we are going to add that to negative 2 times, I'm sorry, radical 2 times radical 3 is going to be negative radical 6. And then on bottom is that 4, the 2 times 2. So there you kind of see the same kind of things going on. That common denominator, the bottom's going to be 4. They're both negative right here, so we'll just say negative radical 2 minus radical 6. You can't combine those. They're just kind of rough. So you're going to get, again, there's that combo. You're going to keep seeing that combo a lot, but now they're both negative. Awesome. So we just found the exact value if I subtracted those two angles. That's super cool. How else is this going to look? Well, sometimes I can't evaluate it all the way out to an actual exact value. I'm just going to clean it up. So let's say I have some angle, I don't know x, but I'm going to subtract pi over 6 from it. So just find the right formula here. This looks like we're doing this bad boy right here. So we're going to take the difference using sine, and hopefully maybe it's starting to sink in. It's going to be the sine of the first angle, which is x, cosine of the second angle, which is pi over 6, and that's sine, so I subtract them. We're going to take the We're going to take the cosine of the first angle here, cosine x, and times it by the sine of the second angle, which is pi over 6. And then let's just see how far we can clean this up. I can't do anything with sine over x, so he's just stuck there. But I do know the cosine of pi over 6 is going to be what? That's just a nice first quadrant thing, radical 3 over 2. And then I'm going to say, ooh, can't do much with cosine x, can I? So he's going to be kind of stuck there. But I can say, what is the sine? That's going to be the 1/2. And what's going to happen here, not a whole lot I can actually clean up. We usually just put the number first. So it's radical 3 over 2 sine x minus 1/2 cosine x. So that's all we can do. Don't freak out if you get a variable in there. We just kind of cleaned it up. We just kind of simplified it. And that's going to be as far as we can go. And that's it right there. So we can just kind of expand things, clean it up a little bit. Awesome. All right, we do have another one to do here. We have another identity, so we got some difference. It's actually the same identity. Check this out. This is called the double angle. Why? Because we're going to double the angle. Fancy that name. So what is it? You don't have to write this down. You can just enjoy this real quick. But this is like saying, hey, I'm going to add the same. If I double an angle, I'm adding it to itself. Like 45 and 45 is 90. So you just double the angle, you add it. So it actually follows our rules here. I'm going to run out of room. But if I add these together, remember how the sine, it's the sine of the first, cosine of the second, which actually is the same angle. And then what happens here? It's the sine of the second angle, which is still alpha, cosine of the first angle, which is alpha. Everybody's alpha here. And what happens here? Well, I've got sine alpha, cosine alpha. Two, you add them together, what do you get? Here's the formula. All that work for this. You get 2 sine alphas, cosine alphas. So that is a double angle. Oh. Cosine alpha. So that is the formula. Write that down. That's the one you need right there. There's the actual formula. So sometimes if you ever see this in when we're taking the sine of 2 alpha, you just rewrite that right there. Excellent. Can we do the same thing for cosine? So again, if you don't want to write this down, but actually, because if you can just remember the addition, the sum identities, then you can find these, like you could actually just do it. So how'd cosine work? Remember, cosine was cosine of the first angle times cosine of the second angle. Luckily, every angle, you can't get this one wrong. Every angle is alpha. Remember, it was plus, so we do the opposite. We minus. We've got sine of the first angle, sine of the second angle. So this one's a little different because here we're actually can times these. Cosine times cosine is actually cosine squared, alpha. And then we've got sine times sine is minus sine squared. So that is the formula right there. So let's write that bad boy in. That's the main one. I've got cosine squared, alpha, minus sine squared. So if you remember the originals, you can derive these and have them so they're good to go. Now we can manipulate these, kind of like we did with the Pythagorean identities. We kind of moved them around. What is cosine squared? Actually, that's a Pythagorean identity, isn't it? So it's really just 1 minus sine squared is what cosine squared is. So if you want to rewrite this as this, 1 minus sine squared alpha, and then you're going to minus sine squared alpha from it. So I'm using Pythagorean identities in here, and that turns into 1 minus 2 sine squared alpha. So that's another identity right there. That's bigly right there. Whoosh. There it is. Awesome. Can we do the same thing but replace sine squared? Sure. Let me clean this up a little bit. So let's do it again. Let's this time replace, we'll say cosine squared. I'm going to write this out. We're going to kind of derive it. And I'm going to minus sine squared. But what is sine squared? Sine squared is really 1 minus cosine squared. So we can do this. This is just another way to write the double angle for cosine. Distribute that negative. What's going to happen here? So I'll distribute a negative, make this negative positive. Then you can add them together. In this case, we actually get 2 cosine squared alpha minus 1. Excellent. Let me just clean this up a little bit. Okay, so here we go. So I wrote this out. These are just all the same for cosine to alpha. You can write it the first one in red, blue, or purple, depending on your needs there. Jot those down, have those, make sure that's good to go. Circle those. Awesome. Now that we have them, all we're going to do is wrap it up here and just use them. So these are, I think, pretty nice to spot because it literally says 2x. I mean, there it is right there. So as soon as you see this, there's only one option for sine. You just plug it in. So we're just going to replace it. Our goal here is to solve a trig equation. So what are we going to do here? We're looking at 2 sine x, cosine x. So we're going to double that angle equals cosine x. And now we're back to old school solving trig equations like we did earlier. Just be careful remembering this. We always like to bring cosine over. I know it's tempting to divide by cosine. We don't do that. All right, so subtract it from both sides. There we go. And why are we just subtracting both sides? So that cancels out equals 0. And what do we have here? We've got this 2 sine x, cosine x, minus cosine x equals 0. So we said equals 0. Then we hope something factors out here, which it looks like it's going to. What do they have in common? So they both have a cosine. So I'm going to take that cosine out. So I'm looking at cosine x is going to be 2 times sine x minus 1. And now I can solve the trig identities here. What's this going to be? I'm looking for, hey, when does this equal 0? When does cosine x equal 0? And over here, when does sine x equal 1/2? Awesome. So remember doing all this fun stuff. Let's just finish it so we have some completion. I can't leave it hanging. I want to make sure we got it. I think I got to use a circle right here. He may be in the way a little bit. Excellent. So just a rough idea of, hey, where does cosine equal 0? Cosine is going to equal 0 up here at pi over 2, down here at 3 pi over 2. So this is going to happen at pi over 2 and 3 pi over 2. And then where's this one? Where does sine equal 1/2? Well, I know sine equals 1/2 at these pi over 6s, and we want sine to be positive, so it looks like it's going to be here and here. So we're looking at this bad boy and this bad boy, which is what? Pi over 6. and then almost a full 6 pi over 6, it's 5 pi over 6. Wow, holy cow. So we can still do trig equations. I'm going to circle all these right here. All 4 of these would work to solve that trig equation there. Fantastic. Last problem here. Cosine is a little trickier when we're trying to, rewrite things. I know I got to use this formula, but I got a couple options here. So I can use any one of these formulas. So which one do you want to use? Well, if I see over here a cosine squared, I probably want to keep it in terms of only cosine. If I can get rid of one of the trig functions, I'm going to pick the one. There it is, the cosine. So let's try it like that. And sometimes it's a little puzzle. You just got to play with it, see what happens. But I'm going to say cosine 2x. I'm going to use this bad boy right here. So I'm going to say times it by 2 cosine squared x minus 1. And that's going to equal 2 cosine squared. So let's see what happens here. I hope this goes well for us. So we can distribute the 3. So I've really got 6 of these bad boys. So 6 cosine squared x minus 3 equals 2 cosine squared x. So now, again, I kind of want to get all my cosine squareds on one side. So let's go ahead and let's subtract these 2 cosine squareds. So we can subtract it from both sides. Whatever you do to one side, got to do it to the other. Here we go. Whoosh, there it is. Subtract them. So that's just 0 over here. Those are going to cancel and give me 4 cosine squared x's, which is nice. Can we go ahead and just add the 3 too? Because I want to get the 3 over here. So let's add 3 to both sides. Come over here and plus 3. So really, what's this going to equal? It's going to equal 3. Those cancel out. That gives me 4. Ooh, this is a lot of work. Still solving. So what can I do here? Divide by 4. Divide by 4. I'm going to run out of room. Can we extend this page maybe? I'm going to need some more space here. Let's get this out of here. Get out of here. And so now what do I got to do? Let's clean this up a little bit. I'm looking at what? These cancel. And I'm looking at cosine squared x equals 3/4. And so I want regular old cosine. So what do I got to do? I got to square root both sides. Square root both sides. Oh my gosh, this problem just keeps on going. So I can say cosine x equals what? Plus or minus. If I square root the top, I get radical 3. Square root the bottom, get 2. Well, that's convenient. That's something I can see on my unit circle, which I have right here. I have a unit circle here. Places where cosine is radical 3 over 2. So that's going to happen at my pi over 6's. And because it's plus or minus, it's going to take care of all of them, which is kind of nice for me. I got to list them all between 0 and 2 pi. So we're looking for what? When x is going to give us what? Let's start at pi over 6. Then I almost make it to 6 pi over 6, so that's 5 pi over 6. I'm on pi over 6 after that, so I'm at 7 pi over 6. And then a full circle would be 12 pi over 6, so I didn't quite make it, so I'm at 11 pi over 6. Love that unit circle. Maybe it should be my Valentine too. It's a toss-up. Trig identities or unit circle. Boy, they both could be a great Valentine. That is a Valentine's Day for you. There it is right there, man. We did everything. I hope that went well for you. Before I go, just want to give a quick shout out to Jackson B and Miss Anderson's class. I don't know who Miss Anderson or Jackson B is, but I really respect the use of the emojis they put into the comment section. So that's pretty sweet. Good luck to you, Jackson B. I hope it's going well. Good luck on the math check. Peace out.